Well, let's look at the problem where we have a open phase. We have two conductors two phases that have load in them. One phase that's open, and we have a neutral. And the question is, what's happening in that neutral? We're going to use ABC phase sequence. We basically have 10 amps flowing in phase A at 0.8 lagging power factor and 6 amps in phase B at 0.6 lagging power factor. So what we want to look at is what will be the neutral current. If you look at this diagram real quick, you'll notice that it's implied that the neutral current is equal to the sum of IA, and IB. It is, except we've got to pay very special attention to this node. And don't forget Kirchhoff's current law. Basically, it says the sum of the currents at a node have to equal to 0. So we write the node equation here where all the currents are equal to 0, and I'll show you that in a moment. So the first thing we want to look at is basically, given the two loads, what is the angle of the current to the voltage that caused them. For phase 1 or for phase A, it's going to be 36.9 degrees. For phase B, it's going to be 53.1. We're going to arbitrarily use phase A as our reference. We could use anything as our reference, because in a power problem, all you're doing when you establish a reference point, everything is established reference to that being 0. But if I wanted to choose something else, I just rotate all the vectors around by that number of degrees, and they still have the relative position to each other as they did before. So normally we use a phase A voltage as our reference. So voltage A to neutral is what we're using here. We were given that IA and IB equals a 10, and we found it at minus 36.9. But where'd the minus come from? It's because it's a lagging power factor. So both of them were lagging, so both of them have a negative angle.